With no further ado, let's ask Cope Plastics to come on up with our first presentation today, which is a metal replacement application, and get the first of three going. Welcome, Cope Plastics.
Thank you very much. Can you all hear me? You know, I do about 75 to 100 engineering seminars with our salespeople and our sales engineers every year. And it's anywhere from 8 to 100 engineers. This is a lot more intimidating when it's with your peers. So my name is Garrett Birch. I'm the National Sales Engineer for Cope Plastics. I'd like to first thank IAPD for inviting me here, along with Joe Seidel. Joe Seidel is the actual sales engineer with Cope Plastics that came to me and we talked about this application. We invited Joe, but he's actually in Canada fishing now, so he couldn't make it. So I get to do it all myself. I've got 15 years in, Joe's got 10 years in. He's a great guy to work with. I'm going to show the application video that we submitted to the IAPD. I'm going to talk a little bit about how MD Ketron Peak became the material of choice for this application, and then we'll have plenty of time for questions and answers at the end. So with the people in the back could run up the video. It might take a couple seconds here.
Here you see the Ketron MD metal-detectable bearing solution 304 series stainless steel shaft with a two-part component made of bushing. This is a close-up of the 304 series stainless steel shaft assembly, showing a little closer edge detail of the two-part bushing assembly. The customer was using a two-part bushing assembly specifically for the reason to try to increase the extended part life as much as possible. They were having premature failures earlier with the bushing due to fusion welding because it was not lubricated. This application was a higher temperature under load, and it runs continuously without lubrication and is using similar 304 series stainless steel. Thus, the two-part bushing was an attempt by the original manufacturer to get longer life. That did not work. Here you see a typical two-day failure, which happens when two parts fail and fusion weld, causing assembly failure. This creates a lot of damage downstream, as well as food contamination from metal. This was also a primary reason for the requirements for plastic components. Here you see a similar 5-day fusion welding failure of the same current metal component. The video here is showing fabrication of our existing plastic bearing assembly. This part is used by a food producer that has now developed a food product for the US and many underdeveloped countries. The food product developed using this processing system has substantially benefited the world market. Exact parameters of the application were researched by the sales engineer to meet the customer's exact requirements. Requirements that we had to meet for this application are the following: metal detectable material, FDA compliant, very heavy loads, temperature requirements to 375 degrees Fahrenheit, unlubricated, and to be a minimal mating component to limit wear as much as possible. Here you see the current 304 series stainless bushing assembly and the very first prototype of the Ketron MD polymeric bushing, also showing detail of where we went to a one-piece design and eliminated the need for two pieces, thus simplifying it and making it better for service life. This is a detailed close-up of both metal and polymeric bushings, again showing the detail of the one-piece assembly versus the two-part metal assembly. This is our first prototypical Ketron bushing with a stainless steel shafted component that is still in service. Here you can see our current polymeric bushing and the metal assembly with the shaft and the current design bushing assembly. sample material came from Jim Evel at Quadrant, which at the time was the only material available in North America to test the material out of. The picture here is showing the polymeric detectable bushing test fit. This is when we initially made it and tested it to the stainless steel shaft to see how the fit was for the interferences. Shown here is the stainless steel housing and the end of the extender nozzle that the assembly goes into, which is also the same extender assembly that was shown in the failures earlier. This is the day we actually tested and press fit the bushing into the extruder assembly. Here we are testing that the press interferences were correct. Here we show the press actually being fit at the time. It went in with the correct amount of interference press fit, so the bearing would not spin in the steel housing. Here is the bushing after being pressed in. The interference was correct with the amount of press fit tolerance on the OD of the component, as well as the ID as it goes into service. And finally, we are showing the stainless steel shaft as it is being put down into the bushing to make sure that the interference on the ID was correct, giving just the amount of proper running clearance. Even though this was shown at ambient temperature, it was also calculated in the thermal expansion factor for when it is actually running at the elevated temperatures. Your vision, our quality, one partnership. Cope.
I also want to give a special thanks to Jenny Reed and her voiceover model that did the voiceover for us. They did a very good job for us. One thing that I also wanted to mention before we move on, that when you saw the fusion weld of the two metal parts, that cost the end user $10,000 in food loss because of metal fragments that were going into the food product, and about $2,000 in parts and maintenance costs of tearing the equipment apart. After their third failure, they shut everything down and called Cope Plastics to come and help them with their problem. We had done an engineering seminar there probably sometime in 2012, and they didn't have any immediate needs for us then, and that's when we introduced the metal-detectable UHMW, the metal-detectable acetyl, and the metal-detectable nylon materials. Some of the information that we had to go and gather from them to make an educated assumption on what we could use is we had to find out what the load was. The load on this particular application in this bearing was 62 pounds per square inch. The velocity, the housing that the bearing was pressed into rotated at 200 feet per minute. The temperature was 375 degrees Fahrenheit. What the customer was processing through this new design was a soy-based breading material for the world food industry. It's a healthier base than the corn base that we traditionally see in the United States, and they're processing a soy-based breading that's being sold here in North America and overseas. We needed an FDA-compliant material. We could not use any food-grade greases because it would contaminate the breading. We needed continuous service, 100% duty cycle, 24 hours a day, 7 days a week. We wanted to find a dissimilar mating part that was unlubricated. We needed to be resistant to chemical washdowns. And lastly, they needed a metal-detectable material. Well, we really didn't know where we could go with this at first, because we figured the 62 PSI and then the velocity of 200 feet per minute, it gives us a PV value of 12,400. Ketron Peak 1000 has a PV value of 8,500, but with the 4-to-1 safety factor that's incorporated into the material, we knew that we were fine with the PV that we were at 12,400. The temperature of 375 degrees, we knew that the Peak 1000 would be fine at 480 degrees. But the one thing we didn't know if metal-detectable Peak was available at the time. That's when we called Quadrant and talked to their technical service people, and Jim Hebel said that it is available in Europe, and he happened to have some at his desk that we were able to get to the customer. Normally, we like to have testing time on these types of opportunities, but the customer wanted something as soon as possible because they were down. The press fit dimensions that we used on the peak bearing is much different than of metal. The press fit we used on the bearing is 14 thousandths, which is a little bit heavier than normal press fit tolerances that we use, but we didn't want any foodborne particles to get between the housing and the bearing itself. The ID clearance on the shaft was 35 thousandths. A normal clearance that we would use on a part like this would be right around 31 thousandths, but we needed to add about a 4 thousandths clearance because of the elevated temperatures. This MD filled material was the first material that we sold to this customer. Now they're looking for other applications within their plant, and it's really shown them that the metal detectable materials in these applications are very, very good, and they continue to look for other applications within their plant. Any questions at all? One other thing before I conclude, the customer now has 15 lines running these bearings in their facility. They do shut them down every 7 days for maintenance, and unfortunately, they've only replaced 2 of the bearings since these have been running for 6 to 8 months now. Any other questions? Yes.
Can you hear me?
Yes.
Did you have to take into account bore closure when you
Yes.
press fitted in the bearing?
Yes. Normally on nylons and the softer materials, we double it and add about 6 thousandths. On this one, as you can see, on the 35 thousandths, we've got the press fit of 14 thousandths, so you multiply that by 2 to give you 28 thousandths. And then we added another 4 thousandths plus the regular 3 thousandths that we usually give for clearance on the ID of the bearings. I have all these cheat sheets that I can use, but a lot of it's in my head. Any other questions? Thank you very much.
All right. One more round of applause for Cope Plastics, please.